And polar coordinates are used in real-world applications. I mean, one thing we'll see by the end of the lesson, that there's times when you have equations that are not functions in rectangular coordinates. Actually, in polar coordinates, they are functions, which is good, meaning that for every value you plug in for the independent variable, you only get one value out for the dependent variable. The other thing, and this is just giving my experience, which is always related to the weather, right, is that when you're trying to forecast for the Earth, right, you're trying to forecast for a sphere, it's not in 3 dimensions, it's not polar coordinates, it's spherical coordinates. But, it's similar. Instead of having an r and a theta, you've got an r and a theta and a phi, where one of the angles is the latitude and one is the longitude, and the r is the distance from the center of the Earth, basically, right? That's spherical coordinates. Right? The problem you have when you're trying to model what's going on is this is the way the weather works, right? How forecasting and modeling the atmosphere works. Every day, 2 or 4 times a day, depending on where you are in the world, mostly over land masses, they send up weather balloons. And the weather balloons, as they're going up, are transmitting data back, which are telling the pressure and the temperature and the winds and the humidity. And, it's irregularly spaced, first of all. It's not over water for the most part. And, it's mostly where there's population. So there's a lot more in the eastern United States than there is in the western United States. Okay, then what happens when they start going up in the air? It's not like they stay fixed over that spot on the Earth, right? The wind blows them a certain distance. You end up with a very irregularly spaced set of points that you actually have weather observations for. Maybe there's an ocean in between, right? You take that, and then it's actually a science to say, well, how can we best take that and make an evenly spaced grid of points? We actually don't know information from all these points. We know them about these points. But we take this data and we assign all the values to a very well-spaced grid. It's usually like 1 degree latitude, 1 degree longitude. You get another point in your model, right? And then you're going to use those. That's the initialization of the model. And then you're going to use your 7 equations and 7 variables and let them run forward in time and make the forecast. Most of the stuff you see on TV, is coming from this. Now, the problem is that if you're trying to do this on a global scale like this, you've probably done some mapping in a science class. A Mercator projection of the Earth is where you kind of lay it all out in a rectangle like that. And the equator is probably the middle. And maybe, 0 degrees longitude, which is Greenwich, England, that can be the middle, right? But what about on the ends? I mean, where is the leftmost point on that rectangle and where is the rightmost? I mean, most of the time it's taken at 180 degrees longitude to one side and a negative 180 degrees to the other. But in fact, that's the same place, right? It is exactly the same place. It's the middle of the Pacific Ocean. Now, when I take this data and I put it here, at the beginning, I mean, I could have like a perfect sine wave or something like that. And sure enough, the value that I get at this point is going to be exactly the value that I get at that point because it's the same spot on the Earth. It better at least start the same. But when the model goes forward in time, now what's going on at this side may not be the same thing that's going on here. And pretty soon you've got 2 different values for all those temperature, pressure, and winds for the same spot on the Earth, which is not good. Right? So instead of using rectangular coordinates, we use spherical coordinates, which don't have that same problem. There's no discontinuity in a sphere. It's just a continuous, circle as you go around. There's never a point that you're going to have a different solution on one side as the other. It just continues. So that's why we use spherical coordinates, and that's, we could take that back to 2D. That's why we learned about polar coordinates. You'll notice that actually that is kind of what the shape of the graph would be. It'd be kind of like a sine wave, something that we've studied before.